Hi, I'm Veli from Greenwood Solutions. Today we're going to be talking about surge protective devices, lightning, inductive loads, transient voltages, and anything else that potentially can harm electronic and electrical components in your home or factory. Now, if you like what you see, hit that subscription button. Let's get stuck into it. Bang! Oh, was that a surge? So one of the things with surges is that components can be damaged. Photovoltaic systems can be damaged by both direct and indirect lightning strikes and over-voltage disturbances caused by electrical switching operations, load switching, and so on. Now, specifically in regards to lightning, there is a lightning map, and there are some areas of Australia that receive a lot more lightning than others. And in those particular locations, you'd be silly not to incorporate some kind of surge protective device. Darwin, for example, is the lightning capital of the world. So if you were going to do a ground mount solar system there, you'd sort of be a little bit crazy not to include surge protective devices. And statistics on damage due to lightning-induced overvoltages have shown that electronic installations up to about 1 kilometre from the lightning strike point may be susceptible to induced or line-carried overvoltages. Equipment can be damaged by either direct lightning strikes to the structure, kaboom, direct lightning strikes to the power lines, or from indirect strikes caused by cloud to ground or cloud to cloud strikes. Now, these latter events cause induction and earth potential rises. It should be noted that transient electrical disturbances similar to lightning may be caused by power switching operations, in other words, inductive loads and power line faults. So what actually happens in the case of a solar ground mount system? When lightning strikes a solar PV system, it causes an induced transient current and voltage within the solar PV system wire loops, in other words, the cabling. These transient currents and voltages will appear at the equipment terminals and likely cause insulation and dielectric failures within the solar PV electrical and electronics components such as the PV panels, the inverter, control and communications equipment, as well as devices in the building installation. The combiner box, the inverter, and the maximum power point tracker device have the highest points of failure with a solar PV system when it comes to these events. Now, what standard do we look at? Well, effectively we look at AS 1768-2007, and there's two basic scenarios. Buildings without external lightning protection and buildings with external lightning protection. In most cases, the building does not have any lightning protection at all. And this is the case of commercial buildings that solar panels are usually installed on. We use surge protective devices, or SPDs, both on the DC, so that's from the solar perspective, and on the AC side as well. The SPD for the DC input to the inverter and solar array must be designed specifically for DC applications. So you can't put an AC surge protective device into a DC situation. AC surge protecting devices are not suitable because upon failure, their disconnect circuitry may not quench the arc. AC SPDs rely upon a voltage zero crossing to quench the arc, a sine wave situation, which does not occur with DC, obviously, so the arc may persist with the possible hazard of fire. There are three types. Type 1 is the first line of defense. It's installed in the main switchboard of the facility, and it protects from external factors causing voltage spikes. Type 2, second line of defense. This is located in the distribution board, protected from voltage spikes caused by switching of loads like motors and lightning events. Type 3 is the last line of defense, so we're talking electronic devices and other sensitive loads are protected. All critical loads should be protected by this surge protective device. So now we're talking AC. The surge protective devices that you select must have a particular rating, and so you're looking at the voltage rating and also the nominal current and the max current rating as well. And there are slight differences between the DC SPDs and the AC SPDs that are out there on the market. We have to select whether it's a DC or an AC application, single or three-phase. We have to look at the nominal voltage of the system, so is it 230, 400 or 1000 volts for solar. We have to look at the voltage level protection. We have to look at the peak value of the current that the surge protective device can withstand and function after 15 surges. And then we look at the current max, and this value should be higher than the maximum short circuit current of the electrical network. So there's a little bit of maths involved, but fairly basic. Now in the case of a commercial solar system, the DC SPD goes between the string protection, DC isolators and the string fusing in the inverter. SPD is connected in parallel to your system and the output is connected to earth. One of the interesting things about surge protective devices is how many you put on a length of cable. So there's a relationship between a length of cable and how many surge protective devices you actually install. Cable length between the SPD and the load should be kept short as possible. Damage from overvoltage increases with cable length. If length exceeds a certain point, it's recommended to use a second SPD. So there's some mathematics in regards to the relationship between voltage and cable length and how many SPDs you need to use. Conclusion. SPDs are there to divert the potentially harmful effects of lightning and load switching. For DC protection only, specific DC SPDs may be used. There are three main types of SPDs available. Whether SPDs are used or not depends on the geography, geology, and the presence of sensitive loads. Thanks so much for watching our presentation on surge protective devices. I'm Veli from Greenwood Solutions. If you like what you see, hit that subscription button. That allows us to continue making these videos. Bye for now.